Good afternoon. Please follow along as we discuss the basic refrigeration cycle of a comfort system. Now, some key points we will be discussing will include the following: the compressor and heat exchangers, expansion valve and orifice or piston type of metering devices, the basic air conditioning cycle, the reversing valve and its basic operation in a heat pump, the heat pump cooling cycle, and the heat pump heating cycle. So as we start taking a look at our basic refrigeration cycle of an air conditioning system, remember there will always be three basic components that never changes. You're going to have a compressor, you're going to have an outdoor coil, also called a condenser, you're going to have an indoor coil that's going to be called an evaporator typically. Now it should be noted that the outdoor coil is designed to reject heat from the conditioned space to the outside area of the home where it's not going to be objectionable. The indoor coil or the evaporator will be absorbing heat from the air passing across the evaporator coil and providing a cool air into the conditioned space. Now it should be noted that coils have to be clean in order for the refrigeration cycle to operate properly. In addition, whenever we design our ductwork, we want to make absolutely certain on the inside or on the indoor unit that we design our ductwork for 400 CFM per ton of cooling. Let me say that again, 400 CFM per ton of cooling effect. So if we have a 2-ton unit setting outside, we have to make sure that we design our ductwork inside for 800 CFM. If we have a 3-ton unit setting outside, we have to design our ductwork inside for 1200 CFM and so on. So it's important that we design our ductwork and we provide 400 CFM per ton of cooling on the indoor unit. In addition, it's extremely important that the coils have to be clean if they're going to do their job. So every heat exchanger in the world has to be clean in order for them to do their job. Finally, on the indoor unit, don't forget that a clean air filter is extremely important to maintain the integrity of the duct system and the airflow quality. So as we take a look at the basic refrigeration cycle, we have a compressor and we have 2 coils, indoor coil and outdoor coil. Now as we start talking a little bit about those components individually, what is the compressor? The compressor is designed to compress low pressure cool vapor into a high pressure hot vapor refrigerant. Now note, it's critical that cool vapor returns to the compressor in adequate quantity to cool the motor windings. Thus, suction line size is very, very important. So this can't be overstressed. The compressor is designed to compress cool vapor into high pressure hot gas. In doing so, it's going to generate a fair amount of heat on the windings, and because it's a hermetically sealed system, it's totally sealed. There's no internal fans or anything like that inside, and so the compressor depends on cool gas coming back from the evaporator coil on the suction line to cool the windings. So it's very, very important that our charge is proper. It's very important if we have a piston on the indoor coil that is properly sized. And so there's a lot of factors that can affect that. But the big thing is we have to make sure the coils are clean and that they are providing, and you're providing 400 CFM per ton for cooling effect on the indoor unit. The outdoor coil rejects heat and condenses high pressure hot gas into a high pressure warm liquid. So again, the hot gas from the compressor goes to the outdoor coil, and that hot gas is condensed into a high pressure liquid. The indoor coil absorbs heat from the air passing across it and boils low pressure saturated liquid into a low pressure cool vapor. Now let's go ahead and add a device called a metering device as we take a look at the refrigeration circuit, and we'll pipe all this up together in just a minute or two. So a fourth component is going to be a metering device. We have to have something that'll meter liquid refrigerant into the indoor coil. Because remember, team, you can't just take a liquid and just dump it into the indoor coil. You have to meter it. As you meter that refrigerant, and as you spray that liquid refrigerant into the indoor coil, it's going to drop the pressure as well as the temperature. So really, the expansion valve, it will always be located near the evaporator or the indoor coil. That's going to meter or spray high pressure liquid into the coil. The resulting pressure drop will turn that high pressure liquid into a low pressure saturated liquid, and really what that means, there's going to be liquid and vapor present at the same time, and then that low pressure saturated vapor or liquid will start vaporizing or absorbing heat from the air passing across that coil, and as a result, it'll turn into a low pressure vapor. Now, team, when we talk about boiling refrigerant in the evaporator coil, let's stress something here. When you think about something boiling, you think about something being hot. But now remember, refrigerant, the actual refrigerant, commonly called Freon, in the system is a specialized chemical that's going to boil at 60 below zero for 410A, at 42 degrees below zero for R22, and at about 40 degrees below zero for 407. And so the point is that when we talk about boiling refrigerant in the evaporator coil, you have to remember when we're boiling that refrigerant, it's going to be very cold comparatively. And so even though it's boiling, it's going to be 30, 40 degree temperature inside that coil, even though it's boiling at a particular temperature based on pressure. As we take a look at an expansion valve, let's take a closer look at an expansion valve. This is a type of metering device, and as we see on the left-hand side of the expansion valve, liquid refrigerant will come in on the liquid line and will go past a valve and seat assembly, and will spray that liquid refrigerant into the evaporator coil. Now, it should be noted some of the design features of the expansion valve. You're going to have a sensing bulb that's going to be attached to the suction line leaving the evaporator coil. And inside that sensing bulb is a refrigerant. Now, team, it is not the same refrigerant necessarily as what's in the system. It's a totally sealed system. So the sensing bulb has its own little sealed system where you have refrigerant in the sensing bulb. And as that sensing bulb changes temperature, it's going to exert pressure on top of the diaphragm, which will drive the valve open. So the main thing from a basic refrigeration cycle we have to remember, the expansion valve is designed to maintain a given flow rate into the evaporator coil over a wide range of temperatures. And so the expansion valve is really an automatic or a self-metering type of metering device in the fact it'll maintain a given amount of refrigerant flow into the evaporator coil over a wide range of temperatures. So from a application standpoint, expansion valves always give superior refrigerant control over a piston. The other type of metering device that's commonly found in the air conditioning industry is what we call a piston or an orifice type of metering device. Now, it should be noted there's going to be three components to this body and distributor and liquid line adapter assembly. So what happens is this. From the factory, you'll have a liquid line adapter. You may have a piston or an orifice to put inside of a body or distributor. And then you'll bolt that assembly together. Now, it should be noted that the orifice or the piston is nothing more than a piece of brass with a hole drilled in it. Now, it has a special design so that it will actually seat inside the body or the distributor and allow that liquid refrigerant to go through the middle of that orifice, and based on the size of that orifice will determine how much refrigerant is being sprayed into the evaporator coil. So unlike the expansion valve or the TXV that we just talked about, the orifice is a fixed device. It's just a fixed metering device. It has an orifice or a drilled hole in the middle of that orifice or piston assembly, and it's fixed. It does not change. It doesn't change as far as metering capability through that orifice. The only thing that will change the amount of refrigerant into the evaporator with an orifice will be not temperature, but the pressure on the liquid line. As the pressure goes up, you'll spray more refrigerant through that fixed orifice. As the liquid pressure goes down, you'll spray less liquid. So one of the things about a piston or an orifice, it's going to be the flow rate on that orifice is going to be dependent on the pressure on the liquid side, which is in direct relation to how hot it is outside. So now watch this. The hotter it is outside with a piston or an orifice, the more refrigerant you're going to spray on the indoor through the orifice and into the indoor coil. However, with an expansion valve, like we spoke about earlier, it's going to automatically meter refrigerant based on the temperature of the evaporator. So always remember, the expansion valve gives superior refrigerant control over a wide range of temperatures over the piston or the orifice. Now, some of the advantages of an orifice or a piston are the fact it's very simple. It's a fixed metering device. There's nothing really to go wrong. There's nothing mechanical to go wrong with it. It's just a hunk of brass with a hole in it. Very, very simple, very reliable. So if we have our refrigeration cycle, again, you know, if we could have a piston or an orifice, and it will be located near the evaporator coil, and it also is going to meter or spray refrigerant, high pressure liquid into the coil. And again, the resulting pressure drop will turn that high pressure liquid into a low pressure saturated liquid where you have liquid and vapor together at the same time. And we're going to boil that refrigerant off in the evaporator as we absorb heat that passes across it from the airstream, and then the resulting cool vapor will then go back to the compressor on the suction line to cool the compressor windings. So let's kind of pipe it all together right now in this slide. So we see we have an indoor coil, we have an outdoor coil, but let's start at the compressor. We see from the compressor we have a hot gas line coming from the compressor to the outdoor coil, where that hot gas is going to be condensed into a warm, high pressure liquid. That liquid will then go down through a filter dryer where it will be filtered and dried. That filter dryer actually has some screens in it, but it also has a desiccant material to absorb any moisture that may be in the system. So that liquid refrigerant goes through the dryer, down the liquid line, and then it will go to a metering device. It could either be a TXV, or thermostatic expansion valve is another name for it, or an orifice. We then spray liquid refrigerant past the metering device into the indoor coil, where it boils that refrigerant off into a cool vapor. That cool vapor then goes back down the suction line, back to the compressor, and that completes the refrigeration cycle for a straight AC unit. Now again, it should be noted the coils have to be good and clean, and the charge has to be proper, because remember, team, we want to make sure and get that cool vapor back to the compressor to cool the compressor, because the compressor is a sealed unit, and the only cooling of the compressor that's going to be effective is going to be the cool vapor on the suction line coming back. So let's kind of activate this and kind of get it going. So as we can see, with our basic air conditioning cycle, we put some arrows there to kind of give you a visual understanding. So on an air conditioning cycle, that hot gas is coming from the compressor to the outdoor unit. The liquid is going down the liquid line to the indoor metering device. The indoor metering device sprays that liquid into the indoor coil, where it boils off into a cool vapor. That cool vapor comes back on the suction line, where it's compressed in the compressor again. The compressor takes that cool vapor and squeezes it and compresses it into a hot gas, and you can see the cycle just repeats itself. What we need to understand is we absorb heat from the indoor unit in the evaporator coil. That heat is going to be contained in the refrigeration cycle, and then it will be rejected outside where it's not objectionable. So the basic air conditioning cycle that we see right here, featuring a TXV, is designed to move heat from the conditioned space to the outdoor where it's not objectionable by way of the refrigeration cycle. We see that if an air conditioning system has an orifice or a piston in it, it's the exact same mechanics. It's just that we've replaced the piston, or we've replaced the expansion valve with a piston, and the piston does the exact same thing. It meters refrigerant into the indoor coil. And what we mean by that, we're taking liquid refrigerant and we're spraying it into the indoor coil. And then the resulting pressure drop and temperature drop will result, and the indoor coil will be much cooler than the outdoor coil as we pass air across it and we condition the space. Let's talk a little bit about a heat pump and the difference between a heat pump and an air conditioning system, a straight air conditioning systems. Now remember, team, the main difference between an air conditioning system and a heat pump is the reversing valve. The reversing valve is designed to flow hot gas refrigerant either into the indoor coil or into the outdoor coil based on the mode of operation. Now please follow along as we discuss the gas flow through the reversing valve and how it will change the mode of operation with a heat pump. So the reversing valve is designed, again, to divert hot gas to either the outdoor coil in the cooling mode or the indoor coil in the heating mode. And the reversing valve, internally, it has a slide and some slots within that slide that's going to divert hot gas and cool gas back to the compressor depending on the mode of operation. So as we take a look at the cooling mode of operation at the top of our screen, we see that hot gas from the compressor will be diverted to the outdoor coil. And in the cooling mode of operation, the outdoor coil is actually acting like a condenser coil. And we're taking that hot gas and we are rejecting the heat off the hot gas and turning that hot gas into a liquid. We then bring that liquid into the indoor coil and spray it past the metering device. It could be a piston or a TXV. We then evaporate that liquid inside the indoor coil in the cooling mode, and then the cool gas comes back to the reversing valve. It loops through the reversing valve and back to the compressor suction in the cooling mode. Now look at the lower graphic. We see that in the heating mode of operation, we're going to switch the reversing valve, and we're going to take the hot gas from the compressor and divert it to the indoor coil in the heating mode. Now remember, team, in the heating mode of operation, the indoor coil becomes the condenser coil, and it's going to be hot, and we're going to reject heat from that condenser coil inside in the heating mode on a heat pump, and we're going to condense that hot gas into a liquid on the indoor coil in the heating mode. That liquid will then come back down the liquid line to the outdoor coil, and in the heating mode of operation on a heat pump, remember, team, the outdoor coil is acting like an evaporator. So we're going to spray that liquid refrigerant into the outdoor coil where it's going to absorb heat from the outdoor air, and then that cool gas from the outdoor coil in the heating mode will come back to the reversing valve. It'll loop through the reversing valve back to the compressor suction. Now this is a very, very important concept. All the reversing valve is doing is diverting hot gas to the indoor coil in the heating mode and hot gas to the outdoor coil in the cooling mode. In addition, you'll notice that the compressor suction line will always remain the same. It'll be in the middle. And then based on the mode of operation, we may have cool gas coming back to the compressor from the indoor coil in the cooling mode, or we may have cool gas coming back from the outdoor coil in the heating mode. Now this is an important concept. A heat pump does not reverse cycle with the compressor. It reverses cycle between heating and cooling with the reversing valve, as we've discussed. Now let's look at some of the location of system components on a heat pump. So starting out at the compressor again, we see we have a hot gas line going to a single line on top of the reversing valve. In the cooling mode of operation, that hot gas is diverted to the outdoor coil, where that hot gas is condensed into a liquid, and then it goes up and through a bi-flow TXV. Now when we talk about a bi-flow TXV, what we're talking about is a specially designed expansion valve that will meter refrigerant in one direction, but allow refrigerant to flow freely out of that valve with a check valve circuit in the other direction. So in the cooling mode of operation, the bi-flow TXV outside is not metering refrigerant. What it's doing, it's allowing the liquid to pass through a check valve circuit internally, down the liquid line through a bi-flow filter dryer, down the liquid line to the bi-flow TXV inside. Now inside the bi-flow TXV in the cooling mode of operation, its check valve circuit will be blocking the liquid from going directly into the indoor coil and forcing it through the expansion valve system and spraying that refrigerant into the indoor coil. So remember, a bi-flow TXV is designed to meter refrigerant when the liquid's coming in one direction and then allow it to flow freely in the other direction based on mode of operation. So once we spray liquid refrigerant into the indoor coil in the cooling mode, we'll boil that refrigerant off just like we did before. That cool vapor will then come down an indoor coil vapor line. We'll loop it back through the reversing valve back to the compressor suction. So as we take a look at this, we see this is the basic heat pump refrigeration cycle, and we're showing it in the cooling mode of operation. So let's take a look at that a little bit deeper. So one more time, we've got in the cooling mode of operation, the hot gas from the compressor is going to be diverted to the outdoor coil. The liquid from the outdoor coil will then pass through a bi-flow metering circuit, and the bi-flow TXV is actually going to be going through a check valve circuit and flowing freely. It'll go through a bi-flow TXV. It'll then go through a bi-flow filter dryer, which allows liquid to flow in both directions on a bi-flow filter dryer on a heat pump. That liquid then goes into the indoor biflow TXV, which is acting like an expansion valve. The check valve circuit is closed, and we're forcing that liquid through the expansion valve circuit, and we're spraying that liquid into the indoor coil, where it's going to boil off and absorb heat from the air passing over the coil. The cool vapor will then go down the indoor coil vapor line to the reversing valve. It'll loop through the reversing valve and back to the suction. So in the cooling mode of operation, we see that the indoor coil is cold, the outdoor coil is warm, and the outdoor biflow TXV is allowing the refrigerant to flow freely out of that coil. Now let's switch modes of operation. We see in this mode of operation we have hot gas from the compressor going to the reversing valve now, but now hang on a second, we're in the heating mode. And so we're now diverting that hot gas from the compressor to the indoor coil, which is acting like a condenser. And so as we put that hot gas to the indoor coil, we're going to be heating the indoor space with that warm or that hot gas in that indoor coil. And so in the heating mode of operation, the indoor coil becomes very warm. It's like a condenser coil now. But because it is acting like a condenser coil, the liquid leaving the indoor coil has to go through the biflow TXV on the indoor coil, which now its check valve circuit is in play. We're going to allow the liquid to flow freely out of that indoor coil. We're not going to meter it now. We're going to let it flow freely through the check valve circuit in the heating mode of operation. You'll notice that we've reversed the direction of flow in the liquid line, which is perfectly normal on a heat pump. This is why we have to have a biflow filter dryer. The filter dryer has to allow liquid refrigerant to flow in both directions. So we then bring liquid down the liquid line through the biflow filter dryer in the other direction. And now we go to the biflow TXV outside. Now please notice that the biflow TXV outside, the check valve circuit is now closed outside, and we're forcing that liquid refrigerant coming back on the liquid line to the biflow TXV outside. We're forcing that liquid through the expansion valve circuit outside. We then spray that liquid refrigerant to the outdoor coil, which is now cold in the heating mode, and we're absorbing heat from the outside air and boiling that refrigerant off and absorbing heat from the outside air. We then bring that cool vapor from the outdoor coil back to the reversing valve, and we loop it through back to the compressor. So the very unique thing about a heat pump, team, remember, a heat pump allows you to use the refrigeration cycle for the heating mode of operation in the wintertime, but you also use the refrigeration cycle for the cooling mode in the summertime. So the real advantage of a heat pump is it allows you to use the refrigeration cycle for both heating and cooling. In addition, a heat pump is more efficient electrically than just running heat strips. And so the heat pump really gives you some nice energy efficiency, because now you're utilizing the refrigeration cycle for both heating and cooling year-round. And instead of just burning a heat strip in an electric furnace, for instance, the heat pump will greatly reduce the amount of energy used to produce heat over just a heat strip, or over just a heat strip inside the furnace. Okay, at this time we would normally have questions, but because this is a recorded session, we want to thank you very much for your attendance today, and please, we encourage you to look at this basic refrigeration cycle anytime you perhaps have a new employee, or if you're a new person into our industry. Please take a look at this and kind of get an idea what the refrigeration cycle is all about. As always, on behalf of our Winsupply host and our Johnson Controls Champion team, we want to thank you for training with us today and listening to our recorded sessions. Please be safe and have a good day.